series of videos will be about Section 5.5, exponential functions and investing. First, we need to make sure we know some investment terms. Compounded annually means the interest is added to the amount at the end of each year. The future value is the amount to which the investment grows over a period of time. The present value is the original amount invested. The annual interest rate, also called the nominal interest rate or simply the rate, is what percent you're earning each year on the investment. We need to have these variables defined for us. We'll have S stand for future value, P stands for the present or original value, R is the annual interest rate as a decimal, T is the time in years, K is the number of compounding periods per year, I is the interest rate per period, so I equals the annual rate divided by the number of compounding periods per year, and N is the number of equal periodic payments, which is the number of times it's time of payments per year times the number of years. Look at what happens. To numerically and graphically view how $1,000 grows at 6% interest compounded annually, do the following. We make a table that gives the future values of S equals 1 plus 0.06 t to the t for t equaling 1, 2, 3, 4, 5, 3, 4, or 5 years. We graph that function, the given values in A. We graph the function as a continuous function. Is there another graph that more accurately represents the amount that will be in the account at any time during the first 5 years of the money is invested? So here's the table. We've done S equals 1.06 to the t being 0, 1, 2, 3, 4, 5. There's the table. And here's the graph. Now notice the graph is only those points because we're really only graphing these ordered pairs. If we graph the continuous function, we get this. But that's not really true because after 1 year, yes, at 1 year we'll be here, we're really there all the way until we add the interest on here. So this isn't really a true graph. This is actually a more true graph. So we graph it. We start with this amount, and it stays $1,000 till the end of the year. We add on the interest. And you can see this is actually called a step function. Notice it's a piecewise function. A step function, then, on how the investment grows. The future value of an investment with annual compounding. P is the original dollars invested at the interest rate of R per year, compounded annually. The future value S at the end of T years is X equals P times the quantity 1 plus R raised to the T power. If we're going to have periodic compounding, P dollars are invested for T years at the annual interest rate when the interest rate is compounded K times per year. When the investment rate per period is the R divided by K, the number of compounding period is K times T, and the future value results in S equals P times the quantity 1 plus R over K raised to the KT power. Now, if they happen to say, if it's compounded semi-annually, K equals 2. If it's compounded monthly, K equals 12. If it's compounded quarterly, that really means you're going to divide the year into 4 quarters, so K equals 4. If it's compounded daily, we use K equals 365 days in a year. If it's compounded weekly, we use K equals 52 weeks in a year. So those are some values for K that you might want to take note of. We're going to write the equation that gives the future value of $1,000 vested in T years at 9% interest compounded annually. Well, S will equal P times 1 plus R raised to the T power. S will equal our 1,000 times 1 plus 0.09 raised to the T power. This would be our equation for compounded annually. Now, this time we want it compounded daily, so we have to use the other equation. We're using the S equals P times 1 plus R over K to the KT. So S will equal my $1,000 times 1 plus, now this time the 0.09 is divided by daily is 365, and then we're going to raise that to 365 times T for my KT. This will be my formula for compounded daily. We want to do two more things. We want to graph the equations of part A and B on the same axis with T being between 0 and 30. And what is the additional amount of interest earned in 30 years from compounding daily rather than annually? 1,000 times 1.09 raised to x. And our second equation, going down, making this y2, will be y equals 1,000 times, I'll use parentheses for this one, 1 plus 0.09 divided by 365, close my parentheses, raised to, I'll use parentheses here again, 365x, and I'll close those parentheses. Now they ask us to graph it from x being from 0 to 30, and y will start with that 1,000, and not exactly sure how much is this going to grow. We'll go to the 20,000. Hopefully that's enough. This is our first one, compounded annually. And this is the second one, you can barely see it going, compounded daily. So you can see that it grows to be a little bit more. Graph, and you remember we use T being from 0 to 30, and we used from the 1,000 starting to 20,000 for my Y values. And here's what it come out. Now it says, what additional amount of interest earned in 30 years after compounding daily rather than annually? Well, that comes out, and I'll show you how I got these numbers also. But it turns out for the first equation, or for the second equation, the daily, the amount in the account, S equals $14,875. And for the annually, S equals $13,268. Now we started with $1,000, so this is $13,875 in interest. 1,000, this is $12,268 in interest.